Hello everybody. In this video clip I want to discuss with you how we can determine the uncertainty when we make a single measurement with a digital device. And in our case what we want to do is we just simply want to measure the mass or the weight of just a banana using a simple kitchen scale. And what we want to find out is really how much does this banana weigh and how certain are we about this weight. So what we naturally would do is we just simply take our set of kitchen scales and we note it has a digital display here. We press the 0 button and we record that it shows 0 grams. 0 grams without the banana. And when we put the banana on it, we get a reading of 99 grams. So that is how much our banana actually weighs. But does it actually weigh exactly 99.000000000 grams? What is the uncertainty of our measurements? Because that is really important. If we have a very high uncertainty, then, the banana could weigh a lot different to that. So what we really want to find out is the uncertainty of this measurement, and we can write this for this particular banana as 99 gram plus minus, let's call it lowercase u, which stands for uncertainty. We want to know what this uncertainty for this banana, for this measurement is. And actually it depends, strangely enough, on the kind of display that we use, and also the display, and also on the resolution of the scales that we use. How precise can we actually measure things? And usually by convention, this U is nothing else but one standard deviation of our measurements. Now you could say this is really strange because you've come across as standard deviation when we have multiple measurements, but I show you now how we can determine the standard deviation of such a measurement. But before we do that, we need to sort of establish something here. And that is, again, it comes back to the resolution of the measuring device. So we see that our reading is 99 grams. Is it actually exactly 99 grams? 99.000 grams? Probably not, because in this case here, this could be anything between 98.5 grams and 99.5 grams. Because we can see only to 1 gram here, and that is the resolution, 1 gram. So if it was the banana 98.5 grams, it would be rounded up to 99 grams. And if it was just a little bit under 99.5 grams, it would be rounded down to 99 grams. So what we know is that from this display, the banana could weigh anywhere between 98.5 and 99.5 gram. Now what we can do is we can model our display with what is called a probability density function, PDF, so probability density function. And in this case, what we can sort of look at is what is the probability to get a certain value from our reading. What does that mean? Well, we have here our total resolution. Let me draw it like that. And this total resolution would be 1 gram. That is the resolution of our scales. And the midpoint of that was 99 gram. The lower limit would be 98.5 grams, and the higher limit would be 99.5 grams. So we know that the value that the banana actually weighs, the absolutely accurate value, is somewhere between 98.5 and 99.5 grams, but we don't know exactly where it is. So we know, however, that this part here, from here to here, is 0.5 grams. And we have a probability, which is denoted on the y-axis, that all our values that we possibly could get for this banana are between 98.5 and 99.5 grams. We know that if the balance is reasonably well adjusted, there is a probability of 0 that the banana is lighter than 98.5 grams or heavier than 99.5 grams, but anything in between, any value has the same probability, and that is what is denoted with this, what is called a uniform or rectangular distribution. And that is what we have here. And a characteristic of a rectangular distribution is that the standard deviation for a rectangular distribution is given by the equation S equals A, that is this part here, that is our A divided by square root of 3. And this square root of 3, that is just a constant, and you can, of course, derive that mathematically. That is not a huge problem. So we can now write we can express the mass of the banana as 99 gram plus minus A, and that was half of the resolution, divided by square root 3. So that would be 99 gram plus minus 0.5 grams divided by square root 3. And if we put this in a calculator, we would get 99 grams plus minus 0.289 gram. So that is one standard deviation, And we use that consistently to express uncertainty. Now, we have a slight problem here, because here we have 3 decimal places, whereas here we don't have a decimal place. So we need to figure out how many significant figures we can actually use for reporting our result. So the standard rule for expressing uncertainties is that an uncertainty should always be expressed to only 1 or maximum 2 significant figures. So in this case, if we want to express it to only 1 significant figure, because that would make sense, we would say the first significant figure is here this 2. So we would only express it to the 1/10th unit of a gram. And therefore we would write it as 99 gram plus minus, and we round it up to 0.3 grams. We still don't have the same number of decimal places, and what we therefore do is we adjust the number of decimal places of our measurement of our banana to the same number of decimal places of the uncertainty. So our final result would therefore be 99.0 gram plus minus 0.3 gram. And that would be actually our measurement that we are going to report. So the banana weighs 99.0 gram plus or minus 0.3 grams.